lecture is going to be on sound, and we're going to talk about sound as a wave. We're going to talk also about the different types of standing waves that we can generate. What do we mean by intensity? What do we mean by pitch? We're going to be covering all of that today. Okay, so sound is a longitudinal wave, and sound is a wave which can only travel through a medium. And so sound requires a medium to travel. And it is a longitudinal wave. And so when we say longitudinal, what we mean is the direction of the oscillation of the wave particles is in the same direction in which the wave travels. So one way we can kind of understand that is if the wave is traveling in that direction, the particles are also going in that same direction. That's what we mean when we say a wave is longitudinal. A transverse wave, in contrast, this is a transverse wave. The direction of the oscillation of the particles is at 90 degrees to the direction of wave propagation. Now, sound requires a medium. And one question for you is, does sound travel faster in air or in water? So sound actually travels faster in water than it does in air. And sound travels faster in steel than it does in water. And so sound travels faster in solids than it does in liquids. And sound travels faster in liquids than it does in gases. So now that we have the properties of sound out of the way, let's go on to what we need to really focus on for the MCAT. So let's talk about this. Let's talk about intensity. What do we mean by intensity? So intensity is actually power over area. And so the units for intensity are joules per meter squared second. And so when we say a sound wave has a specific intensity, this is what we're referring to, the power over the area. And so that is the first property of sound we need to think about. So now, when we talk about how loud a sound is, what we mean is this. And so, what does this equation mean? What this equation is telling us is that the sound level in decibels is equal to 10 times the log of I, which is the intensity of the sound wave, over I naught, which is defined as 10 to the minus 12. And so the reason we say 10 to the minus 12 is that the human ear can hear sounds at about a minimum threshold of 10 to the minus 12. So 10 to the minus 12 is typically the minimum threshold of sound that we can hear. And that is defined as being 0 decibels. Because the log base 10 of 1 is 0. And so, let's do an example to make this make more sense. So, if we hear a sound that is of 70 decibels, how much energy lands on an ear measuring 0.05 meters by 0.03 meters. So, we know that the sound is 70 decibels. So we can say this. So now let's move the 10 over to divide both sides by 10, and we get this. And so 10 to the 7, if we take the exponential form, is equal to I over I naught. Now we know that I naught is 10 to the minus 12. So 10 to the 7 multiplied by 10 to the minus 12 is equal to 10 to the minus 5. And so 10 to the minus 5 is equal to the intensity of that sound wave. So we've solved for this in watts per meter squared. So, how do we find the amount of energy? Well, this is giving us the intensity, which, if you recall, is in watts per meter squared, which we can say is joules per second per meter squared. Now, if we are taking an ear of 0.05 meters by 0.03 meters, well, if we multiply by the area of the ear in meters squared, that will cancel and will be in joules per second. And so if we want to find the amount of energy landing on that ear, we can pick a time. So we'll say in 1 second. So 10 to the minus 5 watts per meter squared multiplied by the area of the ear, which is 0.05 multiplied by 0.03 times 1 second. And we get 1.5 times 10 to the minus 8 joules. So that is how we can find out how much energy is coming. And so we have just gone over the intensity of a sound wave and how we can use that intensity to measure the level of that sound wave. And we convert intensity to decibels. So when I say loudness, I'm talking about decibels. Okay. Now another thing about sound is how does intensity vary with the radius? So if we take someone who is standing a certain distance from the source of the sound, what is the intensity of the sound that they hear? So, as you go further from the source of a sound, the intensity of the sound decreases. Makes sense. You get further away from something, the sound is less intense. In order to think of how much it decreases, you can almost think of it as a sphere. And when we have a sphere, and that is our sound wave, it's almost like a sphere. And so, when we take this equation for the intensity, which is the power over the area, if someone is standing at some distance away from the sound, which would be distance A, then we can find out, well, what's the intensity of the sound at that distance. And also, if we had someone at distance B, so we want to find out the intensity at B, we'd get this equation. Now, a useful thing here is that the power at A is equal to the power at B. And the reason for that is the following. That is because the same amount of energy is flowing through surface A and surface B. So, what we can do is we can set these equations equal to each other. So the intensity of B multiplied by 4 pi r squared, 4 pi r B squared is equal to intensity at A, 4 pi r A squared. And since they are both equal, we get this relation. We can cancel the pi, and we get this. The intensity at A is equal to RB squared all over RA squared times the intensity at B. So this might be a bit confusing right now, so let's do an example. If James is playing the violin and the intensity of the sound that Jack hears, or is in decibels, and he's 63.2 meters away from James. So James is the source of the sound, he's playing the violin, and Jack hears the violin 63.2 meters away. How much louder is the sound when Jack moves 2 meters away? To just rephrase this question. So there's an intensity at 63.2, and we want to figure out at 2 meters how much louder. Okay. So, using the equation we have above, we have 63.2 meters all over 2. We get 31.6. So the radius has changed by a factor of 31.6. So, that is what we have. So, the intensity, because of this, is going to increase by a factor of 31.6 squared, which is approximately equal to 1,000. So how did we get that? So if someone has moved to 2 meters, and they were at 63.2 initially, that means that the intensity will increase by the factor that the radius has decreased by, or I know it seems like it's increased by, but the sound intensity will increase the closer you get. So essentially, that number here is what we plug in. Because if we did it the other way around, we would say, well, the intensity will be increasing by a factor of 0.02 squared, which would mean that it would go down. So that's not the right answer. So we divide this by this, we get this factor here, which tells us by what factor is the intensity going to increase rather I should say the square of this number will tell us how much the intensity is increasing by. So, the thing is about decibels is if a sound is 10 decibels higher, then its intensity is increasing by a factor of 1000. So here is what we have, this equation. So we have an intensity, initial intensity, that we had at 63.2 meters. Then when we move to 2 meters, it's increasing by 30. And the reason that the decibels are increasing by 30 is because of this. For every increase in the number of decibels, so let's say the decibels goes from 30 to 40, for example, the intensity has gone up by a factor of 10. So if you just remember, if the intensity goes up by a factor of 1000, then the number of decibels goes up by 30. So the intensity of a factor of 1000 means decibels goes up by a factor of 30. You can use the same logic for, well, if the intensity goes up by a factor of 100, then how much does the number of decibels go up by? See if you can figure that one out. Okay, so we've talked about sound and we've talked about the equations, the intensity equation, the decibel equation. Now let's move to the next topic, which will be standing waves in open and closed pipes. So a closed pipe is a pipe that's closed at one end. And if we excite the air in the column, the air in the pipe vibrates longitudinally. And that longitudinal vibration in the pipe causes the air to displace and you get a sound wave. And so that sound wave has a specific frequency. It has a specific resonant frequency as well. So let's think about that by beginning with standing waves. Okay, so if we had a wave, you had a string, and it was connected at both ends, and you plucked that string, you'd get a standing wave. And the reason you get a standing wave is you get one wave that goes from the left to the right, and then it bounces off and it comes back. And then what happens is it interferes with itself. That's how a standing wave is created. So, that's the first thing to know about standing waves, is how are they made. Now, let's talk about the properties of standing wave. So, what we're going to do is we're going to go through a series of graphics. And we're going to go through a series of graphics and we're going to explain what is going on in each scenario. Okay, so if we have a wave tied at both ends, we're going to define this length as L. This is L. And so, in each case, we are saying that from the left to the right is L for the purposes of our video. And so, we have the incident wave, and we have a reflected wave. So let's go ahead and extend this here. Again, so we have 2L here. So you have another L here. And so we have we'll do it in separate colors. So we have a wave that goes like this, and it reflects off, and we get the reflected wave. So I'll do that in a different color. So this is our incident wave in red, and this is our reflected wave. Now, what is a wavelength? Well, a wavelength is the distance between two successive maximums or two successive minimums. And so, let's see. If we were to extend this wave, and we're going to draw our reflected wave in a different color. This is what we have. So what's the wavelength of this wave? See if you can figure it out. I'll give you a few moments here. So the wavelength of this wave is 2L. Why is that? So, let's begin here. When we have this wave, what we want to do is we want to pick 2 points on the wave, such as here and here. And the reason we're picking these 2 points is because of this. If we think about this wave, it is increasing, going. If I had my laser pen, this would be a lot more useful. Let's see if it's here. Yes, there we go. So the wave goes like that, increases, and it decreases, and then it comes back up to finish here. Because if we were going to extend this wave even behind, we want to pick the point which corresponds to that point. So as you can see, this wave, it's increasing, going up that way. So it's increasing, then it decreases, and then it increases again, and then it hits this point. So once it's hit that point, that is the point that corresponds to here. That is 2 times L, right? That is when the wave has began to repeat again. Now let me draw another standing wave. Let's see if you can figure this one out. What's the wavelength of this wave? That was very badly drawn. Let me just draw it again. Okay, good enough. So this is, once again, this is L going this whole way. Now let's see. So let's pick 2 points that correspond to equivalent points on the wave. So the wave is starting from here. We can say, well, it's increasing here, decreasing, and then it increases again and hits here. This is where it hits another node. So what's a node? A node is where the wave is at the midpoint. So when we say midpoint, what we mean is, if we had a wave and we sketched it out like this is a node, this is a node, and this is a node. It's where it's crossing that midline. And so, as you can see, we've figured out this. So what's the wavelength? Well, it's just L, because the wave starts to repeat itself again at a distance of L. In the previous example, what we had is the wave started to repeat itself again at a distance of 2L. Now I'm going to draw another wave, and we're going to do the same thing. Now this is going to start to make more sense in a little bit. So, I apologize for these drawings. They are not ideal, but they illustrate the concept. So, what's the wavelength of this wave? See if you can figure it out. Well, let's do the same analysis. So, the wave increases, then it decreases, and then it's increasing again right here. So the wave has repeated itself at this point. So it started here and it finished here. Now what is that? Well, that is 2/3 L. Now we could keep doing this. So initially we had 2L, then we had L, then we had 2/3 L. So let's do one more. What about this wave? So the wavelength of this wave is 2L over 4, or L over 2. Now why is that? Well, it's the same reasoning that we've done before. So let me just redraw this once again. I do apologize for all the redrawing. Drawing is not my strong suit, and I struggle with it quite a lot. There we go, that's actually better. Okay. So, once again, we have this point here. The wave is increasing, then it decreases, and then it increases again. So the wave repeats itself here. The way you can also tell, by the way, is that it should be symmetrical at this point. And that is L over 2. And so we can write an equation here that the wavelength of this standing wave is equal to 2L all over n. So what is n? N is the harmonic. So this wave that I drew here was the first harmonic, because it's 2L is the wavelength, So 2L over 1, that must be the n value. This one had a wavelength of 2L over 4, or L over 2. So let's sub that in. L over 2 equals 2L over n. So let's cancel the L's. N over 2, just moving that up there, is equal to 2. So n is equal to 4. That is the fourth harmonic. So the equation to tell you the wavelength of a specific harmonic is 2L over n. That is how you find the wavelength of a standing wave. So then, how do we find the frequency of a standing wave? So, we know that the frequency is equal to v over lambda, the wave speed over the wavelength. The speed of sound is 285 meters per second, which we typically approximate to about 300 meters per second. So, what you can do is solve. So let's say we had a standing wave of the, let's pick a harmonic, third harmonic. So we have the third harmonic, and we can say that the value of L was 0.4 meters. Let's say it was a guitar string. A guitar string is an example of a standing wave because it's fixed at both ends. So let's do it. 2L all over n is our wavelength. So it's 2L over 3. So that's 2/3 L is our wavelength. And we know that the speed of sound is 300 meters per second. So it's 300 meters per second all over 2 times L, which we'll say was 0.4 meters. 2L over 3. And so you can compute that and get your answer and see what it comes out to. So that's how standing waves work. Hopefully that makes sense. And it's important to do lots of practice on these standing waves to make sure that you totally understand them. Okay, so let's move back to our discussion about the pipe. When we have a pipe, and it's playing, and we have the wave, we have a couple of cases. We have a pipe open at one end and a pipe open at both ends. How do they differ? So, let's begin with the pipe that is closed